Think forward. Think Research Channel.
The talk is not on frontiers of physics, but it is a talk about daily experiences that we cannot escape. The beautiful things around us, the physics everywhere. And it is that physics and that beauty that we want to carry over to our students. That's the beauty of teaching. When you experience things in nature, it could be rainbows, it could be a sunset, it could be the ocean. Everyone experiences something. Everyone feels it's nice, it's beautiful. But there is so much more, and that is what I call the hidden beauty, and that is the knowledge. And it is that knowledge that doesn't narrow, but it is that knowledge that only widens, that gives us an insight that people who don't have that knowledge don't have. Their experiences are great, but they're always narrow and always shallow, just the beauty. That's all they see and nothing more. In our case, however, we have the privilege as a physicist to see more, and that widens our experiences, and that is where the teaching, of course, has to come in. And today, I'd like to talk to you about some of these daily experiences, and I would like to start with color. I want to ask the simple questions: what are colors and why, and when do we see colors? Now, as a physicist, I can only make a modest attempt. I can make a hole in a curtain, I can let a narrow beam of sunlight through, hits a glass prism, and the glass prism decomposes this light from the sun into colors. Now, light is electromagnetic radiation. Long wavelength, red. Short wavelength, which is blue. Extreme short, violet blue. The prism sorts out the white light into colors. We call that dispersion. So now you may think that the wavelength determines the color, but that's not necessarily true. You would think that if I show you the longest wavelengths possible, that the eye can see that it's always red, and if I show you the shortest wavelengths that the eye can see, it will always be blue or violet. But that's not necessarily true. Let me start by showing you the color triangle, something that most of you should be very familiar with. The color triangle already is quite bizarre because it tells you that by mixing 3 colors and only 3, you can effectively make all others. It's called additive mixing. The red, the green, and the blue. There's no wavelength anywhere in there of yellow light. But yet, if you mix them properly, you can make yellow light. There's no wavelength anywhere in there of purple, but yet, if you want to, you can make purple light. So if we can have the first slide, then you will be able to see this color triangle, and I will tell you how this color triangle has to be used. Let me here very schematically redraw that triangle, but very schematically. And so we would have here red, and here we would have blue, and here we would have green. Now, if you want to make, for instance, this color here, so I put this point here, then you draw 3 lines to that point. 1, 2, 3. And now you have 50% chance that you do it right and 50% that you do it wrong. You may think that you have to put in this much red and this much green. It's exactly the other way around. This is the amount of red that you put in there. And this is the amount of green that you put in there. And this is the amount of blue that you put in there. And then you get sort of that color. So if you go all the way here, where you have yellow, so you're sort of here, well, then you put in this much red and this much green. This is not new to you. The color triangle, we teach students as physicists, and it works amazingly well. Our televisions are based on this. They have 3 electron guns, the red, the green, and the blue, and your monitors at home of your computers have also these 3 guns. And by mixing the intensity of the 3 colors, you can more or less get every color you want to. Now, if you don't set the 3 electron guns properly, then you may run into a problem that the faces that you see may look reddish, or they may look purple or greenish, but that's a matter of a fine adjustment, fine tuning. I have here a box that I can use to mix colors. I have red light, green light, and blue light. So if we want to make yellow, then we have to put in almost an equal amount of red as green. So just give it a shot. We turn on the green and the red. That's not bad. It's yellowish. If you want to make purple, you go all the way here. You have to put in a huge amount of blue and a little bit of green. If you hear, this is the amount of green you put in. So let's try that. Let's try to make purple. So we need a huge amount of blue and a little bit of green. So we turn the green down a little, and you get purple. Nothing new. You're already bored. You're here 5 minutes and you're already bored. You're telling me, look, what are you telling me that is new? Not yet. All right, so we can now turn them all 3 on, and then, you guessed it, you come out somewhere here, and you get some whitish light. So this is all fine, and this is what we teach our students, and most of us can sleep with that. However, life is not that simple. I have 2 black and white slides. You can turn the slide projector slide off. I have 2 black and white slides. They were made by Edwin Land, a personal gift from Edwin to me, which I'm very grateful for. And these 2 slides of a clown and lifesavers are made with black and white film. Keep that in mind. One of them, however, was made through a red filter. So I put a red filter in front of the camera. It's black and white film. I'll show you the slides, black and white, non-negotiable. If I have a black and white slide, and I put in front of my slide projector a red filter, what would you expect to see? Well, if you mix white light with red, then you would expect pinkish and reddish and grayish. But certainly there's no way that you get green or yellow or blue for that matter. And that exactly works out the way that we predict. So I will now show you these 2 black and white slides made by the same camera. Exactly the same situation. No, you're not in my way. This is fine. So here is one slide. This is the slide that was made through a red filter. And here is the one that was not made through a red filter. If I put a red filter in front of it, you don't expect to see much more than pinkish and reddish, and that's what you see. If I take the other one, and I put in front of it the red filter, you expect pinkish and reddish, and that's what you see. If I project the two black and white slides on top of each other, well, for sure, you expect black and white, and that's what you see. But now, I will add the red filter in front of the one slide that was taken through a red filter. Hold on to your chair. You may not like what you're going to see. Isn't this amazing? I mean, this is a shocker. If you're really a believer, you say this can't be. I see in the lifesaver, the third one from the left, I see yellow, I see green. I see green in the fifth lifesaver from the left. The lifesaver on the very right is greenish, and the fourth one from the right, some dark blue, maybe blackish. But certainly I see a lot of colors. And all we're dealing here with two black and white slides and a red filter. If any one of you doesn't see the variety of colors, I really recommend you see a doctor. An eye doctor, that be. So here you see a phenomenon which is quite bizarre. And you can ask yourself the question, well, are these colors an illusion? Well, that depends on your definition of illusion. I mean, they are as real as anything. It's something that happens in your brains. It's the way that the brains process the information from the eyes. I wouldn't call that an illusion. It's as real as you can have it. And yet, we use black and white slides and just a red filter. It's an amazing phenomenon. It was already known in the 19th century, but it's generally not discussed in physics books because we don't know what to do with it. We can't explain it, and so we leave it out. That's one way to teach physics. You recognize that, don't you? Now, I can make you also see colors in a different way, using only black and white, and not even a red filter. That was already known in the 19th century. It's called the Benham top. You see it here. If I rotate this top at a frequency somewhere between 5 and 10 hertz, you're going to see 4 colored bands. Just white, just the light, we'll use this light, just to get it a little bit more your attention. That all by itself is, again, quite bizarre. Even bizarrer, maybe, than what you've just seen. So I'm giving it roughly 7 hertz. And we have to turn this on. There we go. Use your own imagination. I don't want you to see it my way, but I see some rusty brown in the middle, red-brown. The outer one looks distinctly bluish to me, and the inner two grayish, greenish maybe. But unquestionably colors. What do you think would happen if I reverse the direction of rotation? That's a good one, isn't it? What do you think? Just guess. You can only be wrong. So what would happen if I reverse the direction of rotation? Excuse me? Complementary colors. Yeah, that's perhaps close enough. Maybe. What do you say? Yeah? You do this. I like that. Okay, so the red and the green interchange, you think? Not bad. Certainly a B minus. Well, how can anyone guess, let's face it? I mean, who knows what goes on here, you know? So I'll just show you what happens. Keep in mind, rusty brown here, blue here, and some grayish in between. I first have to stop it. And the colors reverse. The outer one is now rusty brown, and the inner one is clearly bluish. And these have sort of reversed. This is not easy to explain, and you won't find this in physics textbooks. In fact, a lot of research has been done on this in this century, even though it was already known in the 19th century. But a satisfying neurophysiological explanation, I believe, is not yet available, although there are many promising attempts that have been made. So much for color. Let's talk about rainbows. Lots of colors in rainbows. We've all seen rainbows. Let's put it this way. We've all looked at rainbows. But have you really seen rainbows? It's a very different question. You've all looked at art, but very few people have seen art. I'll ask you 6 questions. They are simple questions. The first question is, when you see a rainbow, it's a circle. And even though part of the circle is likely to be below the horizon, it is a circle. And so you can pinpoint the center, and then you can measure the angle from the center to the red of the rainbow. And you call that the radius in degrees. Any idea how large that is? Roughly? Or does it change depending upon the time of the day? Well, you've all seen rainbows. What is a color sequence? Is red outside or is red inside? Or does that depend on circumstances or maybe even on your mood? If you see a rainbow, has it ever occurred to you that there is an enormous difference in sky brightness if you compare outside the bow and inside the bow? The difference is enormous, and yet you may never have noticed it. But maybe you have. I don't want to insult you, just trying. Then you can ask yourself the question, is there perhaps more than one bow, 2 or 3? And if so, where is the other one? And if there is a second one, what is the color sequence? Is red outside or is blue inside? And then comes the $64 question for the experts in the audience. Are the bows polarized? I want you to know that I'm very gentle on you, because when I lecture on rainbows, I ask my students 12 questions. I only ask you 6. How many of you know the answer to 6, or think you know the answer to all 6? David, my graduate student, do you? Don't give the answers, just say yes or no.
I thought you meant if I knew the question with the number 6.
You know all 6?
No, not
You're not sure about 6?
Not all 6, no, I know number 6. I don't know all 6.
Oh, you know only 6?
No, I know.
How many do you know the answer to? 4. I asked 6. Who knows 6? Dirac, my other graduate student. You got a good education, man. Yeah. Who knows the answer to 5? 4. 4? I don't see 4. Only David? Yeah, you? Yeah, don't be ashamed. I mean, don't be modest. Come on. In the worst case, you're wrong. 3? 3. 2? 1? Oh, you're honest. I like that. 0. Oh, you are very brave. Very courageous. So, this proves my point. You've all looked at rainbows, but you've never seen them. Now, except for the last question, most answers can be given with high school physics. It's a matter of the proper application of Snell's law, the Dutchman Snellius in the 17th century, the law of refraction. But of course, to do justice to all the questions, and certainly to the 12 that I ask my students, would take an hour. But since you're all physics teachers, I can cut some corners, and so we can go over it a little faster. Now, major contributions to the understanding of the rainbow were made in the 14th century by Dietrich von Freiburg, who was a Dominican and a professor of theology. In the 17th century, Archbishop Spalato in Italy performed experiments with glass spheres, which he filled with water, and many of his conclusions were correct, though not all. A little later, the French mathematician Descartes he was also a philosopher, he gave a highly accurate quantitative description of the waves, but he could not explain the colors. It was not until the 17th century, when Sir Isaac Newton himself looked into it, that he was able to properly explain the colors and the sequence in the bows. We need two conditions to see a rainbow. The first is that we need water drops. That could be rain, it could be spray from a fountain, spray from a water hose. But we need water drops which are directly illuminated by the sun. And they have to be seen from our point of view, away from the sun. So there is the sun. I need water there. Not there, not there, but I need water there. And these water drops cannot be in the shadow of the sun. I can be in the shadow of the sun. That's no problem. But the water drops cannot. So the light of the sun must hit those water drops directly. And if now you do ray tracing, I'll show you some. And if you want to do it really right, you need Snell's equations. But of course, everything comes down to Maxwell's equations. Snell's law is a direct consequence of Maxwell's equations, and so are the Fresnel equations. If you do some ray tracing, then, by simplifying matters, here is a raindrop. And I assume, which is not quite accurate, that the raindrop is a sphere. It's not quite accurate because there's a little flattening because of the air drag. Let's assume here is the sun. And so this one raindrop is hit by sunlight. I haven't drawn the beams here because it's completely symmetric. Everything I'm telling you is axisymmetric about this line to the center of the raindrop to the sun. So you can rotate this around. But I put here some light that hits the raindrop, something here, something here, something here, and then you can go here and do the same on this side. When it hits the raindrop here at an angle of incidence I, some of it is reflected with an L as in lion. Snell's law has nothing to do with that. Maxwell does. Some of it is refracted with an R as in Richard. That's where Snell's law comes in. Sine of I divided by the sine of R equals N2 divided by N1. N1 being the medium where it was, which in this case is air, so N1 is equal to 1. N2 being the index of refraction, in this case of the water. And the index of refraction depends on wavelength. For red light, for water, N is about 1.331. And for extreme blue, let's call it violet blue, we have N equals 1.343. That's what it is. It's about 1% higher. In other words, the speed of light blue light in water is about 1% lower than the speed of light for red light. So we get a refraction there. And so this goes into the raindrop. At this point here, Some of that light comes out. I didn't draw that because the drawing becomes so confusing. And some of it is reflected, with an L as in lion. Well, once you know this angle R here, you know this angle R is the same, this angle R is also the same, and this angle R is also the same. That's just a spherical geometry. When it hits here, the boundary between water and air, some of it is reflected inside the water drop. I didn't put that in, too confusing, and some of it comes out. And it is this journey, penetration into the water, reflection from the back, and then coming out of the water, emerging from the water, that is crucial in the formation of the rainbow. Notice that for this angle of incidence I, this light comes back, and this angle that it makes with this reference line, I call that delta. It's very easy to show, no more than high school geometry, that delta equals 4r minus 2i. You can already smell the 4 r's. There's one r, there's one r, there's another r, there's another r. You have 4 r's right there. That's easy. Let's suppose we start with this light, whereby I is 0. The angle of incidence of this one is 0. If I is 0, then r is 0, and so delta is 0. This is clear. Light goes in and comes back. No surprise. And as you increase I, according to this equation, r will increase, and so delta will increase. And now comes the surprise. If you keep increasing I, there comes a point whereby delta no longer increases but decreases. And the largest value for delta that is possible, no surprise, depends on color. That largest angle for delta, delta maximum, for red light, if I take a perfect sphere, is 42.4 degrees. If you want to think of it as 42, be my guest. If you do it for red, for blue, then you get the largest value is about 40.6. The difference is actually very close to 1.7 degrees. You'll find 1.8 here because I've rounded them off. So if you look at the journey that I've described into the water, reflection of the back coming out of the water, delta can never be larger than those numbers. So if I look at one water drop here, this is now one water drop, and the sunlight strikes this one little water drop here, then there is no light going off in this direction, because that would mean that delta is larger than 42.4 degrees, and that's not allowed for that journey. If you look at delta values which are very small, then all the colors can make it. Red can make it at this angle, blue can make it, green can make it, everything can make it. So the inside of this cone, because this is of course axisymmetric, the inside of this cone will contain white light. No light here, white light here. But if you look at the 42.4 degrees, then only red can make it, because blue is constrained to a smaller cone. And so here you see only red. And if you make the angle for delta smaller, you end up at the blue, and then you get here white light. So this is what one water drop will do for you. And so if you were to project this cone onto a screen, which is what I will later do, what will you see? So I have one water drop, I shine light on it, a cone of light comes back at me, and that cone of light I project on a screen. Well, I will see a red circle, which is the intersection of my screen with this red cone. I will certainly see white in the middle, where all the colors can make it, It will be dark outside. And as I go to smaller angles than the 42, I will slowly approach the blue. Now, how clean the blue is not so easy to predict. But that's what you would see. Is this what we see when we look at the rainbow? No. No. When you look at the rainbow, you're standing outside. And there was the sun, remember, and there's the water, there's raining. There are water drops everywhere. And I see a huge arc there. So if there's a raindrop there, which sends me red light, then there's a raindrop there that may send me white light or send me blue light. So this is not the rainbow, but we are very close. You're here. You're standing here. I'll turn this up a little so that you keep the connection. So you're standing here, and the sun is here. So you're looking at your shadow. By the way, I put the sun now there and not there. Sorry for that. So here is the shadow. This is your shadow. You're looking down. You see the shadow right there. It's raining here. And you're looking at an angle which is quite small relative to this line. It's a small angle. And I look at all these raindrops here in this direction. And these raindrops, all of them, each one of them, throws back at the sun a nice cone, exactly this cone. And the cone angle is 42 degrees. Here's the direction of the sun. 42 degrees relative to this direction. 42 degrees, 42 degrees. 42 degrees, 42 degrees. 42 degrees, 42 degrees, 42 degrees, 42 degrees. This angle is 42 degrees, this angle is 42 degrees, and this angle is 42 degrees. And I'm looking at these raindrops. What color light will I see? Each one of these raindrops is throwing this back at me. I'm looking straight into that cone. Here's that cone. I'm looking into the middle of the cone, somewhere here. I must see white light. Now I look very high in the sky. Here's the sun. I look at these raindrops, zillions of them. 42 degrees, 42 degrees, 42 degrees, 42 degrees, 42 degrees, 42 degrees. This angle is 42 degrees, 42, 42, 42, 42. What do I see? Nothing. Because light cannot make it outside this cone. So the sky will be dark. Now I look at this angle. I look now at an angle which is exactly 42 degrees away from this line. And now you must have guessed it. Now I'm looking straight at the red cone. So now if I draw in this cone, I'm looking straight at this red light. And so I see red light, only when I look at this angle, which is 42 degrees away from this line. And since the whole thing is axisymmetric, I will see an arc. When I look deeper, I see white light. When I look farther out, I see the dark sky. And of course, you can, with some imagination, you can see, if you go a little bit further down, that you may see the remaining part of the rainbow, which is bluish. I'd like to show you some slides first. And before I do that, I want to mention that there is a secondary bow. It's almost always there. You may never have seen it. It is fainter. And the secondary bow is the result of one extra reflection of the light in that raindrop. Newton was fully aware of that. So instead of one reflection that you see in the back there, it makes one other reflection. And that gives a second bow, which is not at 42 degrees away from this line, but it is a little higher in the sky. It's at 52 degrees. Notice also that in this case, you can now predict the color sequence. At 42.4 degrees from your reference line, you will see red. You go a little lower, you see blue, and then you see white. And so when you see the arc, it's clear that the outside must be red and the inside must be blue. So this is the horizon. Here you would see the red bow. This may be the center below the horizon, and this angle then must be roughly 42 degrees. And the blue bow will be here, and here you will have white, and here it will be dark. This is the primary bow. If the sun is alpha degrees above the horizon, if this angle is alpha, then this angle here will be alpha. That point will be below the horizon. Okay, I'd like to show you some slides before I will make an attempt to show you a rainbow. Make it dark. Look at your 6 questions and see how many you can answer. Okay. I need something better than that. Can someone turn on that? There we go. Thank you very much. So here, you see the basic idea, what I've been trying to explain. You see here the light from the sun. You see here one water drop. Refraction, it penetrates into the water, it bounces off the back, and it comes out here. And if you have this angle to be about 42 degrees, 42.4, you would see only red. If you look way inside this cone, here you would see white light. If you look further out, it should be dark. This little water here, if you could make water near your feet, spraying water with a spraying gun, water penetrates the water drop, reflects, and comes out. So you will see actually a complete bow in front of you, even at your feet. But you have to spray water there, of course, which when it rains, that's not the case. But it can be done. I've done that, and I'll show you the result. Okay, this is what Sir Isaac Newton himself did. He made this drawing in his famous book, Optica. And so you see here a zillion of water drops. The sun is here. Here's the eye. This is that reference line that is parallel to the direction of the sun. And the light goes into the drop, comes back, and comes at the eye. And here, this must be red, and this must be the blue. And then he also shows you the secondary bow, whereby notice that the light hits the water drop at the bottom, makes 2 reflections, and comes back. And that gives you the outer bow. And the outer bow, the colors are reversed, which is not so obvious because I didn't go through the geometry with you of the outer bow. But if you spray water around you in your garden, and the sun is high in the sky, then you will see you are completely encircled by a rainbow, red on the outside, blue on the inside, white light here, and no light here. So you see the grass, and you can be encircled with a rainbow. When I first started lecturing about rainbows, this is a long time ago, I wanted to show my students an artificial rainbow that I could make in my backyard in Winchester, where I lived at the time. And so my daughter was spraying water from a water hose she was sending here. And you see water drops everywhere here, also here. The sun was behind me. Now look at the following. Red on the outside, blue on the inside. And look at all this white light. All that white light is the result of the colors that overlap, that they are making it, because delta is smaller than 40 degrees. All the colors can come back at that angle if the angle of incidence I is small enough. But now look outside the rainbow. No light comes back at me, even though there's water here. So you would see this dark sky if the sky is dark and white light inside. This is the huge difference in light intensity. My daughter suffered a lot. This was really a very sad day for her. In fact, it was close to freezing. But I had no choice, because my lectures were starting in February, and this was January. All my kids have sacrificed for science sooner or later. But you get the idea, white light. Red outside, blue inside. Look how much white comes out from here. A lot of water there. Poor Emma. I try to make you see the secondary bow at a 52-degree angle. I succeeded here. You need a very dark background to do that. So this is my driveway. And so here you see the primary, red outside, blue inside. Notice there's more white light here than there, for the reason that I mentioned. But here you see the secondary, and the colors are reversed. Notice that red is inside and blue is outside. It's way fainter than the primary bow. This picture, made by Michael Sorgi in Austria. There is a waterfall here in the front. And that's water, that's all it takes. Look at all the white light here. Red outside, blue inside. And here, no light comes back through this journey, so you see straight through the water drops. There is water here, believe me. No white light. And here's the real one, Socorro, the VLA radio telescopes. This picture was made by Doc Johnson, who kindly gave me a copy. And you see here, the sky is bright inside compared to outside. Red on the outside, blue on the inside. If you look carefully, you see even some dark bands here, which are called supernumerary bows. They are the result of diffraction. Cannot be explained with geometric optics. And here you see the secondary bow, red inside, blue outside. This was meant to show you this supernumerary bows, the diffraction phenomenon. If the water drops become very small, then you get over and above the geometric effect, which is what I just did with the ray tracing. You get diffraction, and diffraction means that light can destructively interfere with each other. It would happen when the water drops become comparable to the wavelength of light, or a little larger. And with some imagination, you can see black bands here, which are the result of this destructive interference. And if this phenomenon is very extreme, if the water drops are extremely small, then it can wash the whole rainbow out. You see black bands, and you see no distinct colors anymore, but the colors begin to overlap, and you begin to see a white rainbow. This is such an example of a white rainbow. This slide was sent to me by a student of mine, Carl Wales. This was taken 80 miles from the North Pole at 12 midnight in the middle of June. And you see there must be extremely fine water drops, not ice. Ice doesn't give you rainbows. Very fine water drops, probably smaller than a few microns. And the bow washes out, becomes white, the colors go away, and you see these beautiful dark bands, which are the supernumerary bows. At least that's the name given to them. Diffraction. Very hard to calculate the diffraction. So now, before I try to make a rainbow, how many questions can we answer? You certainly can answer the first question. What is the sequence? Oh no, the radius. The radius is about 42 degrees. Every rainbow that you see, doesn't matter when or where, the radius must be 42 degrees. To the red. To the blue a little less. Color sequence, red outside, blue inside. Sky darkness, the sky is quite bright inside the bow, dark outside. There are always two bows. The third one is there, but is in the direction to the sun, so that you can never see it. There are two bows always. And the color sequence of the second bow is reversed compared to the primary bow. And now comes the hardest question, whether the bow is polarized or not. Who happens to know whether the bow is polarized? Just that question alone. Yeah?
If there is a reflection, there should be polarization.
Very good. Where's the reflection?
Inside the drop.
Exactly. Very good. The reflection is here. And that reflection, in this case, is roughly at 40 degrees. The reason why I remember that, because if you find the angle delta maximum, and you go back and you find for what angle I that occurs, it turns out that I is roughly 60 degrees. When I is 60 degrees, you get the maximum value for delta. Then this value for R can be calculated with Snell's law. It turns out to be R is about 40 degrees, give or take 1 degree. Now you may or may not have heard of Brewster Angle. But when you bounce light of any surface, whether we go from optically dense to less dense, or from less dense to dense, it doesn't matter. You can have light bouncing off water, light bouncing off glass, but you can also have light bouncing from inside water of air. There is always one and one angle for which the reflected light is 100% polarized. And that's called the Brewster angle. So this light is not polarized, but when it comes back, it is polarized highly in this direction. Electric vectors will be oscillating perpendicular to the blackboard. And so when it comes here, of course, it's polarized like this. This angle turns out to be remarkably close to the Brewster angle for the transition from water to air. The Brewster angle is about 37 degrees. The tangent of that Brewster angle, if you go from water to air, is 1 divided by the index of refraction. Now you can take the average value between these two, and you will find then that the Brewster angle is about 37 degrees. So you're within 3 degrees of the Brewster angle, so the polarization is huge. It's almost 98% polarized. All right, let's try to make a rainbow. But when I'm going to make a rainbow, I cannot do that with thousands of drops, millions of drops. So the only thing I can do for you is to show you that. To use one water drop, I have it here. Ooh. Ooh. Oh my goodness. One water drop. There it is. It's a big one. It's a glass filled with water. And I'm going to shine light onto this one water drop. And what will happen is out comes this cone, which itself is not the rainbow. We discussed that. The rainbow is the result of the superposition of all these cones when you look at the individual drops. Out comes this cone, red here, blue here, white light here, and dark here. And the same is true, of course, completely axis symmetric. This is my sunlight. This is a light gun, which will shine straight at you. And let's see whether we can show you that light from that one water drop. It looks like I did something that I shouldn't have done. Okay, I shouldn't have shown you this because it I'm going to first lower the screen. Turn off the hold it. Stop. Okay. I'm first going to make this rainbow, and you will see nothing. No, I'm first going to make it dark. I want you to get used to the darkness first, because it's going to be very faint. So let's first make it dark. If you can close the door there in the back. So let your eyes get adjusted to the darkness. And now I'm going to slowly lower the screen. And if you are sitting there in the light that is awkward for you, you may want to get yourselves different seats, because this is, I mean, you pay so much money for this that is not fair. Just move. You just move a little, or walk out in that direction. We were aware of this in the beginning. There was nothing we could do about it. Don't sit in the sunlight. Just move to there and you'll be all right. Okay, let's look at it. We see here this cone, this one cone, which is produced by one drop of water. And you see here the red on the outside, the blue on the inside. It's dark here and it's light here. If you go through the geometry of the Brewster angle, then the bow is polarized very strongly here in this direction, tangentially to the arc. And so it's polarized here like so, and it's polarized here like so, almost 98%. And I have a polarimeter here, so I can show that to you. Okay, now I allow this is the way that the polarimeter lets the polarized light through, and I'm going to rotate it 90 degrees, and it gets dark. So you see that the light that comes back from this flask is highly polarized. If I do it here, the angle is different. This is the way that light goes through the polarimeter. I have the polarimeter now at an angle because the direction of the bow is different. And if now I rotate it 90 degrees, I can kill the light. So you see that the light indeed is highly polarized. Not too long ago, I was walking on the beach, Plum Island, with a friend of mine, Bill Pridorsky, and there was water splashing up from the ocean, and the sun was in the west, and every time that the water was splashing up, whoosh, I saw very quickly this rainbow. And I said to Bill, look, fantastic, you know, just whoosh, rainbow, and then it's gone, because the water splashes up and the water falls. He couldn't see anything. And I said, well, look, I'll tell you exactly where to look. So we determined this reference line from the sun to us. And I said, you have to look at 42 degrees away from that line. So if there's no water, of course, then you don't see it. So make sure that wherever that arc is of 42 degrees, that's where you look when the water splashes up. Bill couldn't see it. And then I noticed that Bill was wearing polarized sunglasses. And I don't know whether you've ever given it any thought, but polarized sunglasses are polarized in such a way that this is the allowed direction of polarization, because you want to kill the glare from roads, from water, which is polarized in this direction, for the same reason, the Brewster angle. So polarized sunglasses are polarized like so. But when we were at the beach and the water was splashing up, we saw a bow like this, so it was polarized like this. You know, you see very quickly when the water splashes up, you saw a red band here, and he killed it with his sunglasses. And so I said, Bill, take your glasses off. And then he saw it. Physics works. Now next time, when you see a rainbow, I hope that you will look at it differently, and you will always check from now on that the red is outside and not inside. This is a disease. And you can never kill that disease. You can't resist it. You will also always look for the secondary. And so you will convince yourself that the colors in the secondary are reversed. And you will also confirm that the inside of the bow is brighter than the outside of the bow. Now, if you really want to pass this course, you would take your own linear polarizer, which every physicist, and certainly physics teachers, should always carry with them. Oops, yeah, I have mine here. And so you look at the rainbow, and you convince yourself that indeed it is polarized tangentially to the arc. And all this joy and fun you will have over and above the everlasting beauty of the bows, and you will see much more than people who do not have this knowledge, and whose experience is therefore necessarily rather shallow. Your knowledge adds, your knowledge does not subtract. During the remaining 15 minutes, I'd like to ask myself the question, why is the sky blue, and why are sunsets red, sometimes redder than other times? Light that comes from the sun scatters in the atmosphere of the Earth. And the scattering the cross-section for scattering depends on wavelength. If the particles in the atmosphere are very, very small, a few microns, then the blue light is preferred to scatter over the red light by the famous Rayleigh Scattering Law, namely that the cross-section, or the probability for scattering, goes as 1 over the wavelength to the power 4. So the blue light, very roughly, would have a probability which is 10 times higher to scatter than, for instance, red light. And so what is going to happen now is, if you look here at the Earth, and this is the atmosphere, and here is the sun. That's the direction of the sun. And you stand here, and you look here in this direction. Well, there's no direct sunlight that comes to you, because the sunlight comes from this direction. So the only way that you can see light from that direction is that it must have scattered. Maybe single scattering or maybe multiple scattering, but it must have scattered to you. This is not the geometric optics that I discussed earlier with the water. This is a different phenomenon. This is scattering of fine dust. And since blue has a 10 times higher probability to do that than red, it's no surprise that no matter where I look in the sky, that I will see blue light, highly dominated by the blue. An extra bonus for those of you who have your linear polarizer with you: if you look at the blue sky at an angle which is exactly 90 degrees away from the sun, That's always a great circle in the sky, right? If the sun is there and the sky is here, there's always one great circle which is 90 degrees away from the sun. Then that light is not only blue, but it's also polarized, nearly 100%. You can check that. You should, it's fun. But if you go closer to the sun, it's less polarized. If you go farther away from the sun, it's also less polarized. If there were no atmosphere, if the Earth were completely without atmosphere, the sky would be dark, just like it is on the moon. Because it's only the atmosphere and the dust in the atmosphere and the density fluctuations, the molecular density fluctuations themselves in the atmosphere are sufficient to scatter the light that makes the light come from the sky to be blue. So no atmosphere, no blue skies, and so when you look at the moon, if you're walking on the moon, the sky is black. I'd like to show you two slides which show this in a quite nice way. I came across these slides. One is from an astronomy textbook. It's a picture of the Pleiades, cluster of stars in our galaxy. And these stars have shed off a lot of dust. So they're embedded in a huge cloud of dust. The light from the stars is white light. And I want you to take a look at the reflected light from the dust cloud. So if we can have the next slide again, if you can turn it on. You turn on the... Look at this. Isn't that incredible? You see here stars which clearly, distinctly turn out, produce white light, but it is this dust around them. When it comes to you, the probability of scattering is about an order of magnitude larger for the blue than for the red, and so the blue dominates very, very convincingly. And then I came across another slide which intrigued me a lot, and that is a man walking on the moon. It's this slide. Now look at this. There is no atmosphere on the moon. So the sky must be completely black and dark. Well, that's what you see here more or less. What is this? Any idea? It's blue. That should give you a hint. What is that? Give it a shot.
Is the camera in a box?
Not that I'm aware of. Excuse me? I hear too many voices and my hearing is not too good, so I'm failing here. Yeah, I think that's what it is. That's what I think. It could be wrong. This person is kicking up dust. There's low gravity on the moon. It's very fine dust. And he is just sloshing along there. And he is kicking up this dust. And the sunlight is clearly coming from the right. You can see that. And so this light here must have made a journey towards you. I bet you it's even polarized very strongly because it's nearly 90 degrees. And so you see he's creating his own blue atmosphere that you see around him. When the sun sets, the light from the sun has to go through a tremendous amount of atmosphere. Much more so than during the day. During the day, the light comes in like this. But at sunset, let's suppose that we're talking about sunset and the sun is all the way there, then the light comes in like this through the atmosphere. And so the number of scatterers in the atmosphere increases enormously. And so you can imagine that the light that has been, if you call it filtered, that has been scattered out, that there is absolutely no blue light left here anymore. All the blue has disappeared. Whatever has made it through, if anything, is red. So there is a cloud here. And you look at that cloud. What do you think that cloud will look like? That cloud will be red, because this light already is red. And so you see red clouds. You've seen them all, very common. So the light itself changes color completely so dramatically that by the time that all the blue has been taken out, the sky turns reddish, and you see red clouds in the sky. And I want to show you a rainbow which occurred near sunset, when the sun was already so low in the horizon that when it was raining here, the rainbow was formed, but there was no blue in the light anymore. So what do you think the rainbow looks like? It's a red rainbow, because all the other colors are gone. So let's take a look at that red rainbow. They're very rare. I've seen it only once. The sun has to be very low. Okay, if you can show the next slide. There it is. Isn't that incredible? Only red light. Remarkable. All right, now I'll try to catch a few birds with one stone, and I'll try to create for you a blue sky and at the same time a red sunset. And the way I'm going to do that is as follows. I have here a small glass reservoir with thiosulfate, sodium thiosulfate, and I'm going to shine light through there, which we will project there on the screen. It's a circular hole that I've made, which is my representation of the sun. You see it there. I will make it much darker later on. And so the light goes through this bucket of sodium thiosulfate, which is in here, and there is the light of the sun. And there are almost no scatterers in here. Maybe there's a little dust in there. So that light of the sun is just as white as the light of this light gun. But now I'm going to put in there H2SO4, a little bit sulfuric acid, in here, and then sulfur will precipitate out. Very small particles of sulfur will start off, fractions of microns in the beginning, and they will slowly grow. You will see now the following, that this becomes now an atmosphere whereby the light that comes in this way will be scattered in your direction. Well, which light do you think will make it the best? That's blue light. So you will see that bucket turn bluish for the same reason that the sky is blue. An extra bonus would be for you if you had brought your linear polarizer, that if this light scatters at 90 degrees, which is not the case for you, but it would be the case for you people here, then it's also 100% polarized. Now, I have a polarimeter here, and I can hold it in front of it. So I will be a little kind for a change. So you will see the blue sky, because the blue light has a higher probability to be scattered. As the sulfur grows and grows in size, the scattering becomes more intense. And what is that poor sun going to do? That poor sun is going to lose all its blue light. So what is the sun going to do? It's going to turn red. For exactly the same reason, when you look at night, at sunset, at the sun, you're looking towards the sun, all the blue has been filtered out, and what you end up with is a red sun. So we catch two birds with one stone, and including the polarization, really three. This will turn bluish, it will be polarized, if the light comes in like this, it's polarized like this, in this direction, for those of you who remember Maxwell's equations. And the sun will gradually get redder and redder because the sodium, because the sulfur will precipitate out. So let's put this in. And then we're going to stir, and then we're going to make it very dark. We always try to time this so that it takes a few minutes. So you have to be a little patient, but that's part of the fun. So look at the bucket, if you can. Oh, I can already see the bucket turning blue. Look at that beam. That central beam is bluish. No question. Shall we see whether it's polarized? Boy, is it polarized. Whoa! Whoa! Gee, physics works. Hey, look at the sun. Hey. 5, 6 o'clock in the evening, I would say. It's certainly not so whitish anymore. It's beginning to turn a little yellowish. And my sky becomes bluer. More light is being scattered because the sulfur is now growing in magnitude and also in size. And the sun is slowly reddening. And we let the sun do its own thing, because if I speed it up with a little bit more sulfuric acid, it really can go out of hand. It goes too fast. I'd like you to experience get a romantic feeling. You know, you're looking at a sunset, let's face it. Don't hold back. It's a romantic place, MIT, believe me. Look at it, it's already quite nice. Quite nice. We'll just hold it. Strongly polarized. And we'll let it turn just as red, as brown red as we possibly can. So the beauty is that you're looking here at 3 phenomena which you can explain to your students. You catch really 3 basic parts of physics at once. The Rayleigh scattering, which explains the blue color. If you discuss the dipole radiation, when light starts to excite electrons which vibrate, you can discuss the polarization of the light. At 90 degrees, it's 100% polarized in this case. And then you can also include the reason immediately why the sun is red, because that comes from the fact that the blue light is no longer there. And of course, there comes a time that the sun will set. And that's nothing we can do about. But in any case, this completes at least my romantic feelings. Thank you very much. Thank you. I hope you enjoy the remaining of your stay here.